Okay, welcome everyone. Good morning, and thank you very much for being here today. The event that marks the final stage of the second SARC-BARINet Aerospace Competition is now beginning. The competition is about presenting the best solution to a selected problem involving multiple unmanned aircraft. This competition encourages collaboration between academic disciplines as well as between academy and industry, and is meant as an accelerator in the field of systems research, and specifically collaborative UAVs. It aims to motivate teamwork, facilitate innovation, expand international collaboration, foster entrepreneurship, and channel research into practical use. I now invite Professor Glauco Caurim, chair of the competition, to open our ceremony.
Good morning, everyone. Thank you for being here on these 2 days with us. We are holding this event for the first time here in Brazil. It's a great joy to receive all the teams that qualified for this final stage of the SARC-BARINet Aerospace Competition. The theme this year is fire detection and fighting in forests using multiple UAVs. It's, as most of you know, utmost importance for both Brazil, Sweden, and the whole world. It's also opportunity for us to have you here with us and make you know São Carlos as a center for excellence in aeronautics and engineering. And we are very proud to receive you here and show you a little bit what we are doing today. In these 2 days of the event, we will have activities teaching applied tools and demonstrations of the solutions proposed by the teams that were classified. And also, in addition, we invited some companies to the exhibition, and also for some interactive activities. My special recognition to all of you for being here with us, and also for those of you that are having the opportunity in Brazil and abroad, because we are streaming this event also live today. Hope there are some guys in Sweden that also sharing us this event. Thank you very much, Carlos, and welcome.
Thank you very much, Professor Glauco, for the welcoming words. I'd like to officially thank our sponsors who recognized the importance of this event and who, with their investments, are responsible for its feasibility. We are honored to quote each of them in alphabetical order: Embraer, Inover, Saab. Many thanks to each of these companies that made the competition possible. I'd also like to acknowledge the effort of the organizing committee composed of researchers from partner universities in Sweden and Brazil: Chalmers University of Technology, Federal University of Minas Gerais, Federal University of Santa Catarina, KT8 Royal Institute of Technology, Linköping University, Luleå University of Technology, Technological Institute of Aeronautics, and University of São Paulo. And also the support of the organizations that cooperate with everything to happen the most educational and interesting way possible: Aerospace Cluster in Sweden, Federal University of Paraíba, Foundation to Support Physics and Chemistry, Sweden Brazilian Research and Innovation Center. Now, continuing our event, I have the honor to invite to his words of welcome Professor Paulo Greco, head of the Aeronautical Engineering Department.
Thank you. Good morning, all. As head of the department, I welcome you to our structures. And I'd like to say that this is a very important event for the department, for all of us, because we value very much the student activities, this type of activity. And of course, we value very much the partnership with Swedish institutions and with the other Brazilian institutions. I I would like to thank the organizing committee, especially Professor Glauco, but also everybody involved in the organization of this event. And wish you a very good event, okay? Thank you very much.
Okay, thank you very much, Professor Paulo. I now invite Professor Catalano for his opening words.
Good morning. Thank you for the introduction. Glauco asked me to say some words about the department, the activities we have been carried out in the last years. Then I will try to do the presentation because let's see what happened. Just a second. Sorry about this. Okay, just a second. Was all thing ready? Raffaello was trying to do things there. Was a complicated one. No, it wasn't your problem. It was my problem. So just a second. We'll be there. Okay, still is. Okay. Let's talk about the aeronautical engineering department. In fact, this department is quite new. It has almost 50 years in this School of Engineering. But before that, let's talk about the USP. USP is the University of São Paulo. It's the largest and higher education and research institution in Brazil. we belong, or we placed in almost in the 100 best university in the world, and we have a seven campi, 42 units, and between that we have 4 hospitals, 4 museums. Most of the museums of the state of São Paulo belong to the USP, and 6 specialized institutes. About the courses, we have a 700 regular courses, including 230 undergraduate courses. We have USP is very well known to have both graduated and undergraduate courses in high level. Some pictures here, and the campi. We have São Paulo is the main campi where the rector stay there, so the rectory is there. We are our campi is number 5, of course, the best one. But anyway, all over the state of São Paulo, we have a campi from University of São Paulo. Here in this campus, we have 2 units. One is the center one, where initially started some years ago. In fact, we are, sorry, I'm using, yeah, okay. From this chronology, you see that 1953 was created the School of Engineering here in São Carlos. And next year we be 70 years old. And after that was created the campus number 1, and then some department was migrated to constitute the Institute of Physics, Institute of Mathematics and Computation. And in 1994, the Institute of Chemistry. And in 2002, on demand of the new courses, including the aeronautical engineering, was created the campus number 2. And in 2010, the Institute of Architecture separated from the School of Engineering and became the Institute of Architecture. This is the main, the 2 campus. You can see that the number 1, the area 1, was all crowded. So we have to move to the new one, which is this one we are at the moment. And we stay in the São Carlos city since 1953. São Carlos is very well known as a capital of technology today, but in fact we have 2 universities, the big ones, the Federal University of São Carlos and the University of São Paulo, and also 2 Institute of Research on Agriculture, which makes São Carlos a very unique place. Like you have like numbers of PhD by inhabitants very high compared to the Boston, for example. We are very proud about this. But anyway, this is a fact. Some data from São Carlos. São Carlos is also in a way of the central technological center of the state of São Paulo. It starts in São José dos Campos, São Paulo, Campinas, São Carlos, Ribeirão Preto. This axis, we can, if you start from São José dos Campos and goes up to Ribeirão Preto or even further, this part of the state of São Paulo is responsible for 40% of income tax of Brazil. Also, São Carlos has become a new aeronautical center after, of course, São José dos Campos, where the main plantation of Embraer, which is very big. This is start to become the second place for aeronautics or aerospace. have some companies here. I can list it there. The Airship, the Latam, Autos University, the GPX, where the plant of for testing for an Embraer. Botucatu is another plant for Embraer. It's very near us. So we have a place where we can developing things on aerospace and aeronautics. The São Carlos School of Engineering is, as I said, was created 70 years ago, and we have many courses on engineering. Okay, aeronautical engineering, civil engineering, computer engineering, electrical engineering, and electronics, electrical engineering, energy and automation systems, environment engineering, materials and manufacturing engineering, mechanical engineering, mechatronics, and production engineering. So it's a school of engineering focused on provide to the country engineers of a high level, with a high level education. The activities on aeronautics started, in fact, come from USP in São Paulo, from the 30s or 20s to 60s. Aircraft design was developed in São Paulo, in the campus in São Paulo. Later on, in 1973, they moved it to São Carlos, and they created the same system of they did it in São Paulo, and then we started to think about education after doing some design. For example, this was one of the aircraft was designed. It flew, and the intention of for flying schools. And in 1983, we start to together the people from mechanical engineering, an emphasis on aircraft. Then we graduated like 15 students by year. And finally, by demand of the country, especially the Embraer company, we started the aeronautical engineer course with 4 students a year. There is a difference between the aeronautical engineering and the mechanical engineering. This is specifically for engineering. We form people from aircraft design, all this, anything. In 2010, we create finally, which was a desire from since 1973, the aeronautical engineering department, where we are in this moment. In our course, we have some directives. For example, we try to treat with the students open programs, and they have to developing learn-to-learn capacity. And also, 15 years ago, we started an internship program with the Airbus. So we have international internship for a student to go abroad to learn more how to work in the industry. Of course, we have plenty of internship with Embraer all the time. Also, USP has a large program on double diploma, or people can go abroad to study at the same time. With only on aeronautics, we have 8 universities in Europe to do the double diploma. This is the facilities we have today. We're going to visit these 2 days. And the laboratories, we have a laboratory on aircraft design, aerodynamics, aeroelasticity, computational laboratory, and flight dynamics, structures, aircraft maintenance, laboratories are acoustics. So, they are areas where you're developing some research. All the students also participate in the extra class activities. One of the main one is the air design. The air design is probably, the air design team of the department is probably the best, the most successful team in Brazil. They won several times here, and after that they go to the United States to do international competition. So another ESTA class activity, for example, in human-powered aircraft, there is a aeronautical week developed by the students also. Every year there is a week where they do seminars or the other things on aeronautics. The secretary for aeronautics also developing visits and the other activities inside the campus. I'm waiting for the computer to think here. Okay. Let's see. Topos, you can see a desk from the top here, which is deal with the rockets. Maintenance on aircraft is one of the job, the people who have graduated on aeronautical engineering, you go to the MRO to work on maintenance. And I pass very quickly because our time is not very high. Some research we in course here in our department. The first one on the material, on composite structures, prognosis of composite structures, flight dynamic and control systems. Professor Biginotto can talk to you in the visits later on, but mainly I'm studying the PIO, how the pilots induce some inputs on the flight simulation, and it has a flight simulator with emotion we're developing inside. Here are some pictures about this. We're going to have opportunity to visit. And other researchers on flexible wings, mechanical behavior of materials, then aerodynamics, we have a blended wing body, some non-conventional configuration like box wings, supersonic intake, some MDO designed for non-conventional configuration like this. This is a forward swept wing with canard and dorsal intake. Some morphing structures like, in this case, the winglet morphing, where you can change the camber to increase all the mission using the winglet working not only in one point, but in the whole mission. Some interaction between propellers and pusher propellers and the pylon. Today you have invested a lot on electric propulsion, in this case distributed propulsion systems. Like this is a model. This is a developing technology project with the Embraer. This is the CAD model, and this is the model itself. And we have this simulation doing aeroacoustics and aerodynamic performance, and also using fluid dynamic computation aeroacoustics. This is a power flow software. This is also a simulation with 2 rotors. And also, inside the propellers, we have a system to look at the interaction between 2 rotors, the distance between them, and we measure aerodynamic performance of the rotors, also aeroacoustics with the microphones. Paulo can say a little more about this, but this was one of the projects developing parallel with people from Sweden. It is a known It's an aircraft we can simulate, demonstrate a subscale demonstrator, put in the wind tunnel to see the system from like fly-by-wire, etc., to control in situation of high alpha or other maneuvers. We are also a project on the bigger wind tunnel for aeroacoustics and aerodynamics also. And before that, we talk about, I said a lot of things about aeroacoustics, but we participate of a Brazilian silencing aircraft program. Was a huge program on aeroacoustics developed between Embraer and the research councils of Brazil, for example. This is a kind of triple helix project. That's industry, university, and government. And mainly we trade with the jet noise prediction, fan noise prediction, wind tunnel and flight tests, and also airframe noise prediction. In fact, we develop all the knowledge. We start very, very slowly on the basics, and it goes up to application of noise reduction technologies. This is model inside the wind tunnel with an array of microphones. Swept wings, all treated with high lift systems, which produces more is responsible to produce more noise from the airframe. Also, in GPX near here, we placed the huge antenna array of microphones in the track field here. Then the aircraft pass over there. You measure flyover noise emissions. Also, within these programs, we make a contract with the NASA to see to have a look on the fan noise. We have a rig on fan noise here also, and goes to bigger wind tunnel to measure aeroacoustics, like half model in DNW in Holland, and then the full model also make the testing there. What we do is to developing technology to noise reduction, and then goes to the bigger wind tunnel to see these technologies really work. Also, with the Boeing, we developed a complex nose landing gear for the 777. So we also put there developing 7 noise reduction technology. This is strange because we do a lots of testing with one patent only, so it's quite difficult to develop things. Glauco has, I'm going to explain this. I'm not going to talk too much on these things. Glauco, you're going to, in your visit, explain about these things, about human interaction with robots, etc. And that's it. Sorry about this confusion here, but I would like to say just one word of Glauco. I've been in a high-level group of this, since gripping was sold to Brazil, I've been in this high-level group to decide things between Brazil and Sweden. You know, it's very high pressure, thanks to Glauco, to have people today within the workshop of Brazil, Sweden. We've been trying to do this for long years, so today it's a reality to have you all here. And that's it. I wish you a very good event, and I'll be there for the explanation. Thank you very much.
Thank you very much, Professor Catalano, for your presence and words. We will now, therefore, start the technical activities scheduled for this day. And to start the program, receiving for the opening lecture entitled Development Flying Test Platforms at KT8, the keynote speaker, Raffaello Mariani, professor at KT8 Royal Institute of Technology and director of SARC-BARINet Aerospace Competition. Raffaello, very welcome.
Working. Thank you. And thank you very much to Glauco for inviting me here to be a keynote speaker today. It's very much a pleasure. My name is Raffaello Mariani. I've been at KTH since 2018, so I'm fairly new and fairly young when you're talking about academic talk. And it is my pleasure today to actually present all the work that we have done in the past 2 years, 2.5 years, give or take, at KTH in building, as you will see, something new for KTH they've not seen in quite some time. So, little background I want to talk about. We're going to present very briefly the pre-study that got us here today, the outcome, basically the work that we did. We had decided on a pilot case that was going to be driving us and conducting us to the building of a new research group and to the building of a new education output for KTH. And then once we started working on that one, we were not content with what we were doing. We wanted to look at the bigger picture, the long-term investment for KTH, and that's the bigger picture that I'm going to present. So, in 2019, December, early 2020, January, so right before COVID started, great timing, we were approached by external people and asked, what is KTH doing in electrical aviation? So I looked one another in the eyes like, well, we don't know. So we looked around KTH. There wasn't much going on in terms of the actual aircraft. Some people working on the power grid and so on and so forth, but nobody actually focused on the aircraft. So with that in mind, we figured, let's have a look who's doing what out there so we don't do the same. And we did everything with the pre-study. All right, so what did that give us at the end? It gave us different perspectives, it gives us different ideas, it presented what the world out there is doing on the topic of electrical aviation. The big consortia from the European Union, Emotech, the industry with Rolls-Royce Axel just flew a few months ago the fastest electrically powered aircraft in the world, H-55, the spin-off from Bertrand Piccard Solar Impulse flight. They took an aircraft, they stripped the gasoline, they put batteries in it, yay, we got an electrical aircraft. And then it was still the time then the Airbus Fan X, E-Fan X was still existing. A couple of months later, they killed that project too. More importantly for us, University of Nottingham was a sort of key partner to start the Air Race E, this new air racing class for electrically powered aircraft, very much like Red Bull races, but on electricity. And then TU Brandenburg, they were working a lot on electrical propulsion for aircraft. All right, what's next? When we started really digging into this pre-study, we realized that one word was popping up over and over again. And that word was the big buzzword of 2022, hydrogen. So, MAEPA, another big European consortium project, the Zero Avia, which is a company, US went to England to actually fly the first fuel cell powered aircraft, a hybrid with hydrogen. They made a short flight, landed, congratulations around, next flight, took off, crashed, happens. And then there is this big project from EAG, which is the English Aircraft Group, and they have decided to bypass the whole electrical hybrid, go straight into hydrogen and say we're going to design a 90-plus seater propeller-driven passenger aircraft. And here we go, Airbus with Zero E, all of a sudden, is the driving force, at least in Europe, for this kind of work. But we are neither in the European consortia, we are not a company, so let's have a look what the actual university are doing by looking at hybrid electric propulsion, where the hybridization is the fuel cell, not the gasoline, not the jet A fuel, with batteries. And what we wanted to do was to be able to be multidisciplinary, Because the same people that were sitting around that table looking in each other's eyes as, what have we done, what are we doing, represented, as we'll see in a moment, more than 3 schools within KTH. So all of a sudden the realization, we can actually do everything in-house. Now that's pretty good. So we went for hydrogen, and we've taken a sort of a interpretation of a system of systems concept that seems to be another buzzword right now in aeronautics. And we looked at what other universities are doing. Now, I moved around a lot in this world in the past 20 years, so the first thing I did, I looked back at where I've been. Magma project, which was done at the University of Manchester with BAE Systems, and I believe DARPA was involved, of a flying wing that is fully controlled in flight through flow control, no moving surface if they don't want to. And then my undergraduate in Embry-Riddle in the US, which is basically just aeronautics work, the Micaplex and the Azure, which it's a place for students to meet the industry, startups to be involved with research and academic, with the focus of developing UAVs and aircraft of the future. So now we got, maybe that's where we need to go. Because we're a big university, we have a lot of different skills, a lot of different topics we can study and work on. Let's take the lead into these 3 major examples. So, once we did that, this has really what's out there in terms of the projects, and 2 key past projects. One, the US Navy with the Iron Tiger. They were up and flying for 48 hours with a fuel cell, I believe with liquefied hydrogen. Not really something we can beat at the moment. Georgia Tech is more reasonable for us. We're still talking the early 2000s. They designed a UAV, very conventional in nature, 2 wings, inverted V-tail, and a fuselage, to fly with a fuel cell, and they were on a couple of parts in academia. Right now, 2020, 2022, these are the 2 main projects that we are aware of that are multidisciplinary and expanding. The first one is this hybrid in Holland, which is called Aero Delft. It's a student group, it's a student business, more or like, heavily supported by TU Delft. And the idea is that in a couple of years from now, they want to design a full-scale glider powered by liquid hydrogen fuel cells, put 2 passengers in it, and go around autonomously, people in the plane, not going to fly the plane. From a more research perspective, we have Isée Super-Héros with the Mermoz. What they want to do, they want to replicate the flight by the pilot from Aeropostale Mermoz, from Africa all the way, I believe, down here to Brazil. Anyway, somewhere in South America. My geography is a bit hazy at the moment. And because they know that the fuel cell is not going to take them that far, first of all, they planned the stops in the original flight, but they included the concept of dynamic soaring, so they can use the wind like an albatross to fly and recharge the batteries when they need to. So these are very high projects. And then we figure out what else is out there in terms of testing platforms. 3 come to mind. Again, TU Delft is now basically the biggest aerospace program in Europe, and they have designed for their Navy a eVTOL multicopter powered by the exact same system that we eventually adopted, fuel cells, off-the-shelf compressed hydrogen. Warsaw University recently built a project on flying demonstrator with a big support of Polish Air Force to test research and new technology. And then the Aristotle University of Thessaloniki started about 10 years ago, give or take, with nothing. And with nothing, I mean they had no aerospace department, they had 2 mechanical engineering professors that wanted to build airplanes because they saw the UAV was the future for Greece. So these are all examples that we had in front of our eyes to figure out how to move next. And what we eventually decided to do, we have to look beyond the past and existing work. We need to use a multidisciplinary approach. We cannot just focus ourselves on the aircraft, on the fuel cells, on the control, and call it a day when we're done. And the key in all this work that went on for a few months is people are not just doing paperwork anymore. They are all building demonstrators to prove the point. Because when they eventually managed to enter the large European consortia, what they all had to offer, the thing in common they all had was they were capable of building and flying their own research. Now that really attracted our attention. And that's what we did. So we'll talk about more a little bit later. So based on that, the general overview for us, because university, we need to give an overview, we need to give the right talk for the people to believe in us within the university. We wanted this multidisciplinary approach, and we wanted to look at fossil-free, net zero carbon offset, whatever you want to call it, sustainable aviation from the perspective of the aircraft technology. A lot of work has been done on propulsion itself. A lot of work is being done on air traffic management, on how to improve all the routes, the landing and takeoff, to be able to be greener in a sense. No one seemed to be paying a lot of attention at the full package. That's where we come in. Because we have a very healthy aerospace engineering master program at KTH, although we don't have a bachelor, we wanted to make sure that whatever we're doing in here would directly relate to our education. So these projects became the conveyor to sustainable aviation, future aviation within our academic program. And also, students that before did not have projects where they could work and try their knowledge, all of a sudden they have something to work on in extracurricular activities. You'll see very soon that we don't match the USP here level of commitment when it comes to building and competing. But that's okay. The third pillar in our design, in our big proposal to KTH, is that we need to be able to build a new research group. Again, we have several centers of excellence, 7 research groups that can do one thing, work one piece of the puzzle on their own. That does not seem to be anything aeronautics related that brings them together. Again, the bigger picture. And also be at the service of KTH. Just because a research group did not think before that they needed a UAV, that they could test something on an airplane, doesn't mean they should not in the future. So we wanted to build something that was at the service of KTH research, whether it is environmental, robotics, AI, whatever it is, we want to be a part in what KTH is succeeding in. And then the last part of all this, the fourth pillar, is having academia meet industry beyond the established channels of SAB as a partner for KTH, GKN as a partner for KTH, attract the attention of the full spectrum of aeronautics work within Sweden. Because we are in Sweden, we have probably the country with the most emphasis on the UN goals. No UN goals addressing in your proposal, basically no chance of winning any funding. But it makes sense because it puts our work in a very good perspective, again, for the future. So these are the 5 major ones that we are hitting just with this project. And again, let's not forget the whole driver of this thing. We're going to build a technology demonstrator for future aviation, starting with the first 2 pillars. Because what we had in our hands were 4 people that were very interested in the project, certain number of students that were already on board at a get-go of, do you want to build a plane? But what we did not have at that time was the elephant in the room, which is sufficient funding. Plenty of excitement, 0 money. So where do we start? Education. That's the way forward. Now, the first pilot case, very generic. It is hybrid electric and man-eater vehicle. It was a student-led research project. Again, one of the core of our idea. We wanted to design and develop an unmanned air vehicle. That's not a key thing. We're not there designing the next commercial aircraft. That's beyond what we can do right now. That's beyond what we're interested in. We want to be able to do something when we are asking the questions, addressing them, and hopefully giving information that is going to help answering these questions, all for the benefit of our students as well. So the first case study, we want an aerodynamically efficient aircraft, which could be the aircraft of the future. We'll see what we did. You have a couple sitting here on tripods. Because although we're not looking at designing a passenger aircraft, we want to put the bug in people's ears of what's it going to be in 20 years' time. We can't keep on looking at tubes and wings forever. And that's what most of the projects that we saw at this level also did. Tube, wing, glider type, fuel cell, great, but nothing that looked at the whole picture. And again, as I said, for people, that's us in aeronautics, actually split into two different subsections. The aircraft part, that's me. The composite, manufacturing, and research, that's Professor Malin Ockerman. Chemical engineering, Professor Jonas Lindbergen. He is the fuel cell person at KTH. Then we had machine design, with Professor Lei Feng, mechatronics, embedded systems, energy management. We'll need all that once we build the final airplane. And to address the last pillar, academia meets industry, KTH Innovation, who is the driver for us to talk to future partners beyond the one that are currently established at KTH, is also the place where if you want to get a startup, that's the people you talk to. Now, as anything, we started with the conceptual design phase. We followed the traditional classical design processes. Design requirements, we wanted dynamic efficient. We looked around, most people were flying around 20, 25 meters per second. We wanted to make sure that we could do more than the ones done before, so we set a target of 2-hour flight in terms of endurance. Net zero carbon offset, key thing, your compressed hydrogen fuel cell and the batteries to go along with it. And initial sizing. Now, when we think about it, 25 kilograms maximum takeoff weight, that's a big airplane. 4-meter span, that's a big airplane for a university. But hitting these two targets set us apart from all the projects that we had found that came before us. So, okay, they could be very large wingspan, but very lightweight, never a heavy weight, that's always a bad thing. So we're trying to look at different perspective. And again, this all is to depart from classical configurations. Then we looked at dynamics and the performance. Aerodynamic efficient meant blending with body. Our students actually wanted to go down the route of a box wing. We stopped them because as this is the first project in maybe 20 years that we're doing, we figured let's do something interesting, but let's not do an overkill, so we're going to get stuck and not be able to progress. And the second biggest issue that we found in our literature review was that the fuel cells can operate at a particular temperature range. Now, that's all well and good in a Swedish summer, 25 degrees, you're okay. Go up 500 meters, you're in the right temperature. Try to fly this thing in winter. Your problem is not going to be heating inside the aircraft when you put the fuel cell. Your problem is going to be you got water vapor that's going to freeze, you got icicles inside. So we had to think about the particular problem of running fuel cells in what could be considered an extreme climate. Boeing did it in Spain, very dry, other extreme climate. So we're bringing in the questions. Looked around for the size that we have, 650 watts fuel cell is more or less what we need. 100 watt hours of lithium-ion batteries seems to be doing the trick on a napkin type calculation. And then the structure. Now, everything we've seen so far, you buy the fuel cell, you buy the tank, it's what they call a startup package, put them in. But future aircraft, you cannot simply get a tank, put it in, take it off and fly again. You have to be able to integrate the fuel cell, you have to be able to integrate the tanks in the structure of the aircraft. Otherwise, every one of these tanks is going to be dead weight. And we think about a tank for fuel cells, the one that we have right now, the tank itself, carbon fiber, is 1.4 kilograms. The hydrogen in there, 300 bars, is 80 grams. So once we deplete the hydrogen, we're still going to carry the heavy load, which is one of the problems with the batteries. Once the battery is being discharged, you're still logging along the weight of the battery. So lightweight structure composite designs is going to be key, and thankfully for us, within the Unit of Aeronautics and Vehicle Engineering at the master level, we have a research group in this particular field. And then we have to fly test it. Again, demonstrate what we're trying to do. We're working on a subscale, we'll see in a moment. And at some point, because right now we're still trying to convince KTH that this is something they want to work into, we're going to fly a full-scale model, looking for partners there. Because it's a student project, we thought that could be kind of cool if we give it a nice-sounding name, you know, very CIA type if you want. So we called it the Green Raven. The Green Raven is an homage of the fact that we are sustainable, green, and the ravens are Hugin and Munin's ravens that were looking at the world and bringing messages to Odin. So we brought the Scandinavian and Nordic culture into our design, and the three symbols there are three Nordic runes for air, water, and earth. So bring in, you know, a bit of mythology into the concept. After all, I'm Italian, so must do that. Initial sizing, standard process. But unlike most of the projects that we've seen, our point was not what has been done before in our mission requirements. Our point was what has not been done before in our mission requirements, not what technologies. From that point onwards, same old cycle, go through it, do your analysis, back again the iteration, rinse and repeat until you get something that somewhat flies. Because we are blending the body, we corner ourselves in not being able to use traditional ways of doing things, so reflex airfoils for both the wing and the body. Because we're looking at the aircraft of the future, we're looking at something that could fly transonic, so hey, let's put 30-degree wing sweep just for the sake of it, dihedral angle for roll, and because the very poor performance of our airfoils, we had to add twist in order to be able to improve our stall. We'll see whether that works or not in a moment. And the fuel cell, being the heart of our project, was also the driver for the size of our body. And that's what we ended up with. Now, if some of you aeronautics buff recognize something from the 1930s from the Germans, it was not meant to be a copycat. We just happened to have just about the same shape. But you can see right there, the fuel cell is the biggest volume that we have to deal with. And because of that, that's giving us, as a good side, a lot of volume inside that body to be able to put as much instrumentation as we wish once the airplane is flying, if somebody else wants to test something in it. So, aerodynamics being the core for us at the moment, we started with our students with XFLR5, low resolution, get them started in the process. We must remember that without an undergraduate in aerospace, we had to draw from students that did that abroad, so outside of Sweden, or Swedish students that were starting from scratch with this particular project. Stall angle at 9, ooh, not so good. Maximum lift coefficient, less than 1, also not so good. But they are the consequence of the airfoils that we had to choose. So, we also know that not to work in our favor with XFLR5, the lift is overestimated, the drag is underestimated, the viscous model is not up to par, but at least they give us an idea already of the problems that we're going to face. So we did CFD. It's always easy to get people to do CFD. They really like to work on computers. So look at what people have done before. We have run steady state, K omega, Spilot Almaraz. Both gave us more or less the same answer. You use one over the other if you want to look at the details of the flow or the big picture of the flow. We have a slightly lower alpha stall, not going in the right direction, but still max improves a little bit thanks to better turbulence modeling. The other thing that allowed us to do this initial CFD is that we confirmed that whatever fuel cell we've chosen with the battery that we did in the back of a napkin calculation were in the right range for this kind of aircraft. And that's more or less the pretty picture that we got. So right away, stalls a big problem. The wingtip stalls first. That's not good. We have very complex flow and midspan. Very interesting from a research perspective, not so much from a flying perspective. Thankfully, the big, thick fuselage is saving us from having a very, very dramatic stall. So we got one thing right. But the cool thing is that with all these issues, our students could really keep on developing their skills. So you always have to look at the bright side of a problem. So we decided to go testing. Now, at that time at KTH, the Nordic Wind Tunnel was being used for industrial projects, so we couldn't go right away in it. And we went to the University of Bristol. Part of this is building a research group. Part of building a research group and a research emphasis is looking for international partners that are going to be complementary in our work, that are going to be happy to contribute to our work. And they were the first ones simply because one former colleague now works there. 2021, what we did, we designed the model in-house. It was a master thesis project. The master thesis for us about 5 months worth of work. One student, Alfonso, designed and built the wind tunnel model. Sarah designed the setup because the tunnel in Bristol had a force plate under the floor, but no support for this kind of testing because they used to do half-span type of aircraft. So we had to build everything from scratch, which was a great experience for the students, and we got it working with an automated angle of attack. So we bought ourselves some time, so trying to bring industry standards into this test, instead of every time you undo a screw, you move an angle, you do a screw, rinse and repeat, which can take days just to run one case. So that was also quite interesting. And we had pressure taps in our model, and with that, we actually built it again so that the scanning valve will be inside our model rather than running tubes from meters all the way to the control area. And that helped our production in terms of the amount of results we were able to capture, despite sort of being half quarantined in the UK because somebody on my plane was positive with COVID, although I was not. The beauty of doing things under a pandemic. Once we did that, once we started working on our actual model, we realized that we need to figure out the correction for the support because there were none. So we went for numerical wind tunnel, and that was a challenge in by itself. A student took it aboard himself to do that. He had zero experience in CFD, so he was learning numerics while trying to solve a very complex problem. We went with whatever we knew. We tested the model in the tunnel without support. We get our curves. Curves are good. They compare well with flight. We do it with the support. We know they're going to be different. And of course, both these things are going to have an effect on our flow, which is going to have an effect on our pitching moment. But all in all, we were able to use this data, at least on paper, to correct for the presence of the sting. And therefore, we walked into this test with a bit of confidence. Once we got there, we set everything up, as I said, during COVID. Unfortunately, to go on my own, we did not ship the flow because we realized that our leading edge was already sufficiently rough to be able to be fully turbulent without having a laminar flow at low Reynolds number. Lift worked well. We over-predicted a little bit the lift in terms of angle of attack and in terms of maximum lift, which is good. We know the drag is going to have an issue because the presence of that support is going to increase the drag. And you can see both of free air, the wind tunnel in the model without as measured, the one corrected for the other support. Our problem, once we confirmed the slot characteristic with our tufts, is that the moment just did not make any sense anymore. And what we eventually came to the conclusion of is that, yes, on paper we did the right process to get the correction for the support, but they were nowhere near sufficient or accurate enough to deal with the real model. Unfortunately, due to lack of time, we could have put into place the experimental way to calculate the effects of the support. We had that plan, but as I said, time was limited. But nonetheless, we ended up presenting this at EECAS just passed in 2022. And that's how we were able to share a lot of the grief in going through this project with two different groups, one from Tokyo, blending with bodies, same process and issues we faced, and people that did this numerical wind tunnel as in the industry says, yeah, you guys are where we were when we started. So at least we have some confidence that we are going down the right road. So we went back, did more aerodynamics. That's how we were. So one student took it upon themselves to improve the slope properties, and because we did not want to change the wing itself, we were beyond the last freeze. We were going to keep the plane as it was. The solution we came up with is vortex generators, and not to be like everybody else, we decided to make them aerodynamically shaped and optimized for this particular wing. Did 2.5D simulations, both the course and extracurricular work, and on the airfield itself, it showed that we're doing quite good. So the next step was, let's do 3D, and yes, they work. Unfortunately, we couldn't go test them because by the time we did our next experimental campaign in Bristol, just last week, the model we could work with was a smaller one than the original one that we brought. The vortex generators would have been a fraction of a millimeter high in 3D printing. They would have basically fractured right at the get-go. But what we did more force balance validation, and the data looks exactly like the one that we saw in CFD. So at least we're confirming our work. We brought 2 more students because, again, key is education. You see here both Carlos and Caterina. They are the ones that worked on the vortex generators with the CFD. We want to do some PIV. We're working on getting the results done. We collected something like 4 terabytes of data in 3 days. So the students are hard at work to give us all the information that we need. And my personal obsession, bringing these UAV tufts into an academic environment. I used them in industry. On top of the fact that they're really cool pictures to look at, they give you, because they're so much thinner than what we have originally in the bigger model, they affect the flow a lot less. But all those are techniques that we're trying to also bring into our project. Propulsion, we looked at it. We need to characterize it. One student did a full propulsion analysis, so we know how many engines we need, how powerful, how many propellers, how big the propellers. And then our researchers, postdocs and PhDs in electrochemistry, once they got their hands on the fuel cells, and yes, we were able to eventually buy the startup package from an English company to work with it, they're now going through and debugging the whole system, because we don't simply want to plug it in and fly. We need to be able to do a lot more. So they're trying to beat all the triggers inside the system that has a shutdown when they do something that is not the standard procedure there. But they confirm that that's exactly what we need, and they're having a lot of fun, because all three of them, there were four, one just graduated, they are doing this beyond their actual PhD work. So every Friday they get together and says, now today, finally, we're going to have fun. They get to play with the research rather than focusing on the research. The next thing is flight testing. We're in the process of doing that. Originally, we're going to do in-house manufacturing, foam. Our students in our structural courses are designing that. Then we got a little lucky. We contacted a company in Sweden with whom we work a lot, and they said, sure, we like your plane. Can we give you both the CNC machining and the material? Sure. So hopefully by the end of December, we're going to have the airplane available for us to fly. Being Sweden, it'll be cold, but we still want to fly in early January, but better early February, for one simple reason. You figure out of Stockholm, a little bit of forest in the countryside, nice fields, meter of powdery snow. It's a lot more of a soft crash landing with snow than on hard turf. So, but we'll try to do our best not to crash all the time. So these are key projects. This is the one that is driving us all the way from 2020 to now, and it's going to continue to drive our idea of a new research group at KTH. But we were not going to forget the people that took us there, the faculty that I've mentioned. You can see the students that have been working on that project, and they're not updated. I got another 5 or 6 that just joined. KTH gave us a bit of funding here, a bit of funding there, all seed money to keep us working. Sometimes we were able to talk into a year that was listening to us, sometimes a bit more difficult, a bit more politics to deal with, but at least it got us working so far, and they gave the student a lot of opportunities to work, which then gets us to the bigger picture, and I promise I'm almost done. The one is KTH Aero. KTH Aero is a house or the home for nautical student projects at KTH. We didn't have one as of 2 years ago. Everybody was working in fluid mechanics and aerodynamics, mostly CFD, or they had nothing else to deal with. There comes the Green Raven. Then somebody says, we gotta go to infinity and beyond, because aero, well, for me, is aeronautics. My colleague says, hey, aero is also space. So through the Rexus program, which is a partnership between Sweden and Germany for shooting things up in suborbit, they wanted to be under this umbrella of KTH Aero student projects. And then we have a third project, that's Alpha, that connects the two, because Alpha is an airplane that flies very high looking at the stars. And then what is called FLAIR or KTH Flight, Flying Laboratories for Aerospace Research and Education, and that is our pillar of research in this whole project. The one is called KTH Flight now because KTH is very much short, catchy titles. I still prefer FLAIR, sounds more aeronautics. And it's a new home for research in aeronautics. Directly in purest form, propulsion, infrastructure, we're dealing with hydrogen and electricity. You gotta deal with what's out there in the airports. And also, once we started looking at all that, we figured there has to be a new way to look at integrated transport other than what everybody's doing in urban air mobility. We are behind in Sweden with that. Nobody's really working on it. Sweden values its peace and quiet. Stockholm people in the city center are not going to be fans of big helicopters flying over. At least that's my personal opinion. But what we have is a lot of water around us. So we started looking at something different. Now, all this is to be proven right or proven wrong. Time will tell. But let's talk about the student project. Alpha is an autonomous light platform for high altitude atmospheric imaging. Thank goodness we call it Alpha. It's a collaboration with space and plasma physics, Nikolai Evchenko is the actual driver of that, and then he says, I need a plane. I'm like, okay, what do you want to do? I want to look at the stars. All right? Everybody's looking down. We want to look up because his field of expertise is auroras, sprites, blue jets, and so on and so forth. And he kind of got tired of having a very good day for this phenomena to occur, and on that day you got clouds. Because right now they can look from the ground with telescopes and cameras. When you got clouds, you're not going anywhere. So him being in electrical engineering, lots of students that like to do these things, we brought student project and research project together again. The requirements are very simple in his mind. We want to fly 15,000 meters, a small UAV built by students. We want a cruise velocity of 40 meters per second, nothing really. The range is 300 kilometers. Anybody can do that, right? At night. These things you don't see when you have a nice sunny day. So all the ideas that we have of flying with solar cells, not going to work. Hydrogen fuel cells, not even pushing that far. The original idea was to be thrown with a catapult and climb up. We realized very quickly that by the time we're up, we have 10 minutes flying and then we're gliding. So he says, well, let's talk to the Swedish Space Center in Kiruna, up at the Arctic Circle. They have helium balloons. Let's get dragged up like a fish all the way up to about 20,000 meters. Let's get dropped down. We're going to glide, power on, and then we're going to fly for 300 kilometers. That way we can actually meet the 300 kilometers or 6-hour endurance flight. 7 kilograms what we have to work with, half of which is the payload, undisclosed. We need to have a window looking up. We're looking at the stars. And because the idea is to be able to do this without any support, he wanted a modularity in 1 meter long pieces, because that we can put in crates, put in the back of his car, and drive all the way up north. So this has to be done as rugged as they come when it comes to operations. Problem is, then he says, I also want to fly at altitudes that are standard sea level. So now we have a wing that needs to fly a very low Reynolds number up in 15,000 meters, but very high Reynolds numbers down at standard sea level. Our students were enjoying the design. When we did that, aerodynamics was a big part of this one. Aerodynamic efficiency, of course, had to be one. We didn't stray in terms of the configuration. The focus was not on designing a new idea of an airplane. The focus was on meeting the target of the mission. And for as much as it may pain someone like me, the good old-fashioned tube and high wing works pretty good. We also wanted to figure out the subscale prototypes. We built it in-house. It flew, we were quite surprised, quite well. All this is done by a couple of students that took the models, did the manufacturing, learned the CNCing, learned the flying. We had nobody that knew how to fly an RC plane. We were learning throughout the year to get us to this point. Foam model, because that's cheap and it can be fixed with duct tape. We had to figure out performance, so we got ourselves one of these fancy thrust measurement devices that can measure torque. We did the static thrust measurements. One student in systems and control decided to do a modeling of dynamic thrust. It works more or less. And then we were out flying. We wanted to acquire flight data, not just by going up and taking rounds. We wanted to actually fly a predetermined set of maneuvers to make sure that once we figured out how to do it here in a small scale, when we are at 15K, we know what the aircraft is going to do. Now, the idea was very good. We flew very well for 2 flights, and then our inexperience crashed us spectacularly on the third one. The place was basically dust. We don't know why, except the fact that our pilot who was learning decided to go fly on a very windy day, and that plane did not like it very much. But undeterred, we decided to build the full scale in a lightweight structure design course. This is more of an engineering work, fully mechanical design, the analysis, lightweight structured, manufacturing in-house. There's 14 students working on it. Here are 5 of them. And we built the first prototypes. So the wings were built with plywood, laser cutting, standard spars, cloth like the old-fashioned glider, but we managed to fly by the end of the summer, which was really the big issue for us. Nothing completely out of the ordinary. We met the modularity of the wing, not the fuselage. Once you cut fiberglass, that becomes an issue. So we said, okay, for the first one, Let's keep it in one piece. And we went flying once. I'm not going to show the very embarrassing ending of this video, but the simple fact that we were able to take off, managed to complete one turn, for us was quite good. Again, none of the people there knew how to fly an airplane, either real life or an RC plane. So that gets us to the last 2 or 3 slides, I promise. It's the Catalano plan. The Catalano plan is research. Now, with that, we started again with students a couple of years ago, and we want to design something that flew over water in grand effect. Why? 1, personal obsession of mine. 2, it's a highly efficient aircraft. And 3, technically speaking, the Baltic Sea, it's a great area for this kind of transport if you can figure out how to fly long distances. Now, let's all remember the things that happened in the 70s with the Soviets. That's the idea. The Koreans did something as well. We built it in-house, we did sea trials, we know we don't sink, but we never managed to fly it, again, for that one key factor. We don't have people experienced to do that, and they were too scared to fly something at 50 centimeters off the water at 20-some odd meters per second flight. But that gave us life into research. So now we have a project at KTH as a research project where we are developing a code with the genetic algorithms to design a new, even more efficient wing using laminar flow for this kind of aircraft. That got the attention of some people in fluid mechanics that like to look at little things like turbulence. They said, "Ooh, I like that. Can we do the very low Reynolds numbers?" In the meantime, we took a trip to the US to do research, connections. And then this is the concept of the transport, the new way, the 3rd layer of transport for Sweden, because we think that with the archipelago, this is something that we could push to serve the area of Stockholm and to go beyond the area of Stockholm along the coast. So maybe not the UAM, but something that people are accepting because they are flying on water rather than over their heads. That could be the way. And that got us pretty much here. So I'm very happy because I was able to sell the idea to a Professor Glauco Carino over here, so international export to Brazil, follow Saab's footsteps, why not? And we started working together on this concept. So we provided the CAD. We didn't actually bring the model that we built in Sweden here. It's sitting on my wall. But with the design, the CAD model, and part of the manufacturing experience, we brought that here. And even his team has started looking at everything else in terms of designing a wind tunnel model to be tested here, control system, flight dynamics, and then I think what the part that is most interested in is the embedded system, so we can do obstacle recognition, autonomous flight, and all these things. And that got us to ask us, what's next? How can we use this to, on one end, further research some more, but on the other end, use this as a transition to the real world, to the industry, to a problem that maybe is faced both sides of the ocean here and in Sweden when it comes to surveillance of big lakes, dams, so on and so forth. So using an aircraft that can beat, in theory, actually in practice, the range and endurance of a quadcopter, can still land on water, so you can still sit and take pictures and do sampling or whatever you want to do, but now you can fly faster, farther, for longer. So there's a lot of cool ideas, a lot of good things that we can do with it. And finally, after this long talk, there's 3 words that I would like you to take home with you. Is that 1 is education. That was the beginning of it all. 2nd is research. That's what we are developing ourselves into. And next is demonstrator. We want to prove that we can do it, and we want to use them to further the first 2 words, the first 2 concepts. Are there any questions? Thank you for staying this long with us. Yes, please.
Hello, hello. Thank you very much for your presentation, first of all. But I was wondering, how did you manage so many different students and researchers working on many different topics, and how? It seems like a monumental task to manage everybody.
It wasn't straightforward, that's true. Not Everybody's under my direct supervision, so the fuel cell students, they have their own supervisor. But everything has to do with the design of the aircraft was under me. Nikolai took over all the concept of the electronics and the flying part and so on and so forth. So the first thing was actually, it wasn't difficult to manage the students because the ones that started were the ones that were very interested. I mean, they are the one that chose to blend them with body, it wasn't me. So when you're students that are driven, it's easy to actually manage them. It's actually more difficult to rein them in, not to stray and want to do too many things. And then it became a little bit self-feeding because they brought in the people that they trusted, that they could do the work and they would put this amount of time. The new generation, we're now the third, fourth generation, because every year I get new students coming in and students leaving, they get the feeling that there is a big picture, they want to do it. But yeah, it took a lot of time, it took a lot of effort, very few hours of sleep, because on top of that, when there's teaching and research and all that, and a lot of coffee to keep me going. But I was also very lucky because one person I didn't mention, Boon, full name is Siwatsu Etanakul, from Thailand, he was the very first that joined in. And throughout, maybe willingly or unwillingly or unknowingly, he took the role of being the focus for students to ask. What do I do? Where do I go? Do I need this? So he would filter a lot of the smaller problems simply by taking this experience as a project manager, which is now he's actually using in his real job. Alfonso and Sarah, they were master student thesis, so yes, it took a bit of time, but they had their own supervisor for the manufacturing. I knew them very well. I knew what they were capable of. So it was really choosing the right students all the time. And the one that were not willing to put up the effort and time, within a month or so, they would just sort of drop out. Natural selection, if you wish. But it's also a lot of fun to do that because you can see the students growing into the role. You can see the students being happy in the achievements. I mean, the video of Sarah going, click and go and seeing the actuator moving was the first time she did any of that. So that joy, seeing that smile on her face, the one that keeps you going all the time.
Okay, just raise your hand and I will get you the microphone.
Thank you, Raffaello, for the presentation. You have a very similar problems we've been having here all these years. So we have a lot to talk. So I agree with you. This mainly of this last slide you have, education and everything. So we are very proud of this environment when you have your students involved in the project. Think about CDIO for the construct, design, and operate, for example. This is very, very precious for us. So all those students involved in this project, they are better engineers after all. So, and one question I would like to ask you about, when you did your experiment in Bristol, you have a very different pitch moment problem, but you measure in the same place? Because it's completely different, so
yes.
Maybe it's wrong with different places, I think.
So, on that subject, we believe that the pitching moment is measured at the same location. But we believe, based on what we think CFD is telling us and what I know I'm calculating through the experiment. So that's one thing that we're looking at, and that's why we are redoing the CFD with now Carlos and Caterina, because they're a lot more experienced in using that. I haven't the chance to go look back at the data, but that's the next step, is to take a look at the pitching moment, because when I look at CFD, when I look at XFLR5 and some of the napkin type calculations, they all match. The wind tunnel doesn't. So then you will say, okay, if CFD, XFLR5 and calculations say that, then the wind tunnel must be wrong. It's a possibility, because it wasn't clear exactly where they measured all the force at the moment on the force plate. It could be a matter of 5 centimeters here and there, and all of a sudden you go. The presence of the sting and the actuator, that is going to make a major difference because you have a completely different pressure distribution due to the wake. Now, there's things we can do to change it with hindsight or with a second campaign like that one, maybe trip the actual flow on the sting like I've seen in the industry, try to shield everything with a streamlined shape. These are all things you can say, well, we can do that. But then you have to work with what you're able in terms of time and effort that you have. So the simple fact that with the pandemic, we managed to build it, make it function, go to Bristol at some point and get reasonable data out of it, I'm very happy. And the students are now, Sarah's working at Lockheed, Alfonso is working in Germany, and you are right with these three words. They kept on being asked in interviews about this project rather than have you done that course of this or this course, which is the biggest challenge I have. I have a lot of students that are very bright, but they're very good at following courses. They don't see these projects as an added value until one of their colleagues says, hey, this is a lot more fun than that course, and you learn the same thing. But again, we didn't have that for many years. The only course that we had is the lightweight structure design. So we are rebuilding that mentality of CDIO, which is actually very ironic because KTH was part of that group that started working on it maybe 20 years ago, because my undergraduate in the US, I had that concept. So this is bringing back a lot of things that we used to do and to be able to train again engineers and not engineering scientists. They're very good on their math, but they're missing this hands-on. And now that it's going, I get more and more every year because they want to do things. The wind tunnel, I want to see what we have now with the smaller model, because then we have the corrections with the cylinder, so we can do a more appropriate correction experimentally. And if that matches the first campaign experiment, then I gotta rethink the whole CFD and XFLR 5 location for the CG. If it matches the CFD, then I know that the one that we did had an issue in the measurements, and we're going to sort of backtrack and reverse engineer to find where the problem is.
Yeah, I think it'd be fun to put your model here in our wind tunnel.
Well, that one?
Well, no,
all of them?
Everyone. Yes, the last question, so
Yeah.
just a curiosity. In your model for high altitude research, you're going to use the propellers? Yes. I think the propeller would be more difficult than the whole aircraft, because you can reach a transonic flow. So this is the problem. We're running a propeller in a very thin density, so, and low temperature. Mach number will be very, very low. Sound speed very, very low. So propeller will be probably operating in the transonic phase, so this will be quite challenging. Yes.
We're hoping that we're not going to make it to that point with our aircraft, but we are very aware that we cannot just go. I mean, right now we just went to an RC store, bought the props because we're flying at sea level. But we are very aware that there cannot be the solution once you are at 15,000 meters. You need to choose the right propeller. The plane was supposed to fly 15K by the end of this year. Is it going to happen? I'm hoping, but it all depends on many factors. Propellers choice, it's something that we have yet to address, because again, we're building the expertise in that field. With my contact in Bristol, which is on the picture in the wind tunnel there, Nick Sun, he works on acoustics and propellers, so he told us, okay, I think I have something that could work for the other project that you have going. If you have any suggestion, by all means, I'm all ears. Because as I said, for the past 20 years, we were doing a lot of courses. The students were doing a lot of exciting work in the thesis in the industries. Some were doing small projects, but nothing that I'm aware of, at least, that we have visible to us in aeronautics that can say there is a consistently run project where the students can participate in. One other issue we have is the space where to work. We have to share with everybody else. We don't have a lab for ourselves. We don't have necessarily, not having an undergraduate, it's difficult to get students to participate in competition. That's how you build the knowledge. The continuity of the students, I get it for a year and a half when I'm lucky. We try to bring in the year 1 and 2, but they're not really receptive to that at the moment because they're afraid that it's going to distract them from their course and therefore their grades are going to fall. So there's a lot of work behind the scene that we have to do to reinstill this concept. We have Formula student that is a big group, but then behind you have Scania. That is, there's an enormous Scania truck on the first day of school that says we're supporting the group. We also need to bring ourselves some visibility in that sense so people can say, hey, well, this is, the industry knows about us. It's not just a student project. So we're working all the steps. It's a long process. When I was speaking to the guy in Thessaloniki, it's like, yeah, you are where we were 10 years ago. So good start, keep working, but at some point, it's all going to happen. It just take time. But
I'll make some question.
yeah.
We have a interest, very huge interest here, and you talk a bit about hydrogen fuel cells.
Mm-hmm.
And there's another famous use of hydrogen that is hydrogen airships.
Yeah.
Hydrogen airship, well, airship configuration as a whole is a very sustainable, it's a very green kind of aircraft, but it is not allowed. Hydrogen airship.
Yeah.
What do you think about it? Do you think it's a path to be followed? Do you think it's something that we must invest efforts?
To be honest, I don't know. The reasons why the hydrogen is not allowed, my chemistry is very bad, but I think it goes up in flames very easily. Yeah, so there is the fear of that happening again. I think there's also part of the fact that maybe they don't see the concept of airships yet. It's one of those things that is facing the same problem of the Ekranoplan in some respect. They have an infamous story behind them, and people don't see the potential in it because the Ekranoplan, people think Soviet, Caspian missiles. And the current situation is not helping our cause. But you think airship, first thing, you Google airship, the first thing is up at the Hindenburg up in flames. So before we manage to bring these type of ideas that are valid and valuable, and there are people in Singapore, I mean, that's what I nicked the idea into in some respect, that are bringing these small Ekranoplans as a business case for luxury transport in the Singapore Strait Islands. You need to break that barrier of, is it safe? Because that's also one of the reasons why, if you think about it, we've been talking about blending in bodies since I was an undergraduate, and I graduated in 2003. That, I'm not that old, but dates me a little bit. Yet we haven't seen one. Why? Well, it's difficult to pressurize, it's difficult to build, it's difficult to fly. The airports are not going to like it. Are the passengers going to like it? So there's a lot of things going for these conventional configurations because, and this is something I tell my students on the very first day of their course in Fundamentals of Flight is, you can be the best engineer in the world and design the best aircraft in the world, but if you design a commercial aircraft and the airline doesn't want to buy it, it doesn't matter how good it is. It's still one that goes down in history for good idea, but no. Human factors are a major issue. So when you look at the airships, human factors are an issue. They think, oh, it's going to take me so long to fly there. And the Hindenburg went up in flames. Well, in that sense, we have aircraft crashes anyway. But these are all the things that are stopping us. And if the public is not willing to accept it, the regulatory bodies are not going to spend time on it. Because they probably know there's not going to be a business case for it. Which is one of the incredible things about UAM. Trying to be part of a project now we submitted for the EU on the social acceptance of UAM in Europe. And it's a brilliant case because there's a financial study, has not been proven technology yet, but we're moving forward so fast in it. So all these things that, and I don't know how it is in Brazil, but in Europe the societal aspect has to be taken into account. And all these, new old ideas or old new ideas, people will need to get used to them still. The concept of when you're far from light in a blending wing body. I mean, I was just now on the plane to come here, and I was like, at least I'm on the 3 side on the aisle. I hate to be in the one in the middle seat on the middle 4 seats, because I'm far from the light. And our brains functions that way. Human factors are a major issue. So that's why the technology is important. We need to develop it. We need to remember that we are serving at the end as engineers the reality of things. If we convince the humans to buy on these things, little by little, yeah, then it will work. And I think it's going to happen. The same for the wigs. Doing cargo before we do passengers, they get used to it. Airships do cargo, you prove it works, you prove it doesn't burn in midair, then you bring the people back on.
Thank you. Okay, next one.
So, very interesting presentation. I'm a bit curious about, you mentioned the ECRANA plan that you're looking into, and you mentioned that you're going to run some transport feasibility studies in the Baltic Seas to identify whether that would be an alternative for urban air mobility in that region and so on and so forth. So designing an aircraft, even a conventional one, usually is very expensive. It gets even more expensive. It's even unconventional airframe or propulsion or bit. And an ECRANA plane is likely to be an expensive endeavor, developing it. So in order to have a sound business case for it, you have to have demand. So in your transport feasibility study, did you identify that you would have sufficient demand in the Baltic Sea or other regions in the world that kind of platform could be useful? Did you achieve that number, or?
So to answer your question, we didn't do ourselves a feasibility for the Baltic in terms of the financial. We found the idea from someone in the early 2000s. His name is escaping me. He's from the UK. He actually highlighted, I think, 5 regions in the world. One was the Mediterranean, and the Greeks bought on it. One was the Singapore Strait. So one person as a business owner says, there's an airplane built in Germany for 8 people. Let's try the business case in a country, let's face it, likes to treat itself well. That was the second one. The Baltic was one of the regions. The Caribbean was one of the regions. And then they looked at Australia. And if you look at all these regions, they have a couple of things in common. Mediterranean, Baltic, the Caribbeans, they're all which we can recognize as the limited sea regions. The Baltic and Mediterranean are 2 big ponds. Whether they're seas, they're nice, they're a pond, they're not the ocean. The Caribbean, it's a lot of islands. Singapore Strait, it never gets that bad, then you have highways, and you are, the island of Singapore is sort of circled by a lot of islands all the way to Indonesia. So he made the case that with the right aircraft, there would be a way to use them and make a financial business case. I'm actually trying to follow this guy in Singapore and see if he makes it. For us, the idea is that we want to, what we did, we took the Airfish 8 done by Wigworks, the German company, and we converted that into electrical power. So with an electrically powered existing aircraft, we said, okay, before we say it's going to be feasible with the number of passengers, so on and so forth, can we actually technically do it? So we converted, we used a battery that we found online from now Norfolk, previously Cuberg, and says if we put the battery and we put the motors, and we leave the same motors because there are a couple of Daimler-Benz lorry motors there, how far can we fly? And it's okay, let's make the case from Stockholm all the way up to Luleå, along the Swedish coast. And we realized that if we make it electrical, within 6 hours on a good day, with a couple of stops, we can make it along the whole of Sweden. Then when you compare to the environmental cost, because Sweden is all about the environmental cost, I don't care if it costs them more to actually fly, we're going to be cheaper than an airplane, because to go from city center Stockholm to Arlanda is a train, then the plane, then the car. So we could actually be more environmentally efficient than the airplanes that we have right now. It's about the same time, because by the time you go from central Stockholm to the airport, it's about 20 minutes. You can have at least an hour. Now with the mess and the control, you go out for 3. Then you fly for 1.5, and then it's another half an hour, 45 minutes drive to get to the town. All the towns along the coast have ports almost in the city center, including Stockholm, because we made the case that we want to leave from the Ropsten terminal where the ferries to go to Lithuania, Latvia, along the Baltic are leaving from. So we are looking into an infrastructure that's existing. We would only have to modify part of it. So the numbers work from the technology. We think that as long as we convince the general public that the numbers are going to work financially, it's going to be okay. But we're not looking at investors that are private. Sweden is a socialist country. We are trying to sell the idea to the government. Because if we manage to get Stockholm region and the transport office in Sweden to at least say, okay, now here's the funding. In 2 years, we want to know whether it works or not. It's an idea that we think it's cool. And to help our case, there is one company in Boston called Regent. They're designing a sea glider, they call it, because it actually takes off from hydrofoils. And there's companies such as one in New Zealand that have bought the planes. They actually invested in that plane as transporting the big bays. Brittany Ferries, they want to restore the fast transfer between the UK and Europe because the one that failed with the overcraft. Hawaii bought it to go along the island, around the islands. And the last one, it's one in Split in Croatia because they figure same problem. Lot of little islands that we have to get to, and they might not have a port for something bigger than a small ferry. So there are companies that are buying the idea. And there's a company in Virginia, in Fredericksburg, that are building a cargo version of that concept. So they went again, before we put the humans in it, let's prove that we can carry the freight so people get used to it. So the industry is telling us that there might be a future in this one. The same way the industry is telling us there might be a future in the right environment for UAMs. I mean, a lot of ideas started that way. Will it work? Time will tell. When we started the airplane, people thought, that's a crazy idea. We're never going to fly. Look at us now. So there's a lot of different things. And again, a lot of it's perception from the public. Because even if it financially works, if the public are not willing to step on it, it doesn't matter. I hope we answer your question.
Does anyone else like to make a question? Okay, I think that's it. Thank you very much.
Thank you.
Raffaello. Before I forget, the event schedule is available in this QR code that should pop out here somewhere. And we have a lunch break now. We'll go back 2 p.m. and 5:30 p.m. we have an integration in Area 1, Campus 1. That is a game night, something like that. So good lunch, everyone. And Professor Glauco would like to say a few words.
Thank you very much for joining us during this morning. I think what was quite nice. I have 2 announcements for the groups. If you have any questions, please look for our staff here in the black t-shirts. For the teams, we have reserved rooms for you. There is a room for team Federal University of Minas Gerais. There's also a room for Federal University of Santa Catarina, and also one for our team in the other building. Please feel yourself at home. I would ask at least one representative of each team, and I also would like to ask our jury members here that we're going to make the sequence of presentations for tomorrow, that we decide this sequence, and if one member of each team could join us, and the others have a nice lunch, and hope to see you during the tutorials at the afternoon. Thank you very much.